All right, numbers the right way up. All right. Everyone, hands are okay?
Yeah.
Of the three, yeah, the rest of you.
Honestly, I've dealt with more, so.
Was that last bit?
I said I've dealt with more. I used to work in an outside lawn and garden at Lowe's Hardware, so
Okay.
without gloves, everything is kind of like.
So this was this.
Yeah, it's whatever.
All right, so Nathan and Brian didn't have a chance. I've done this with a much bigger difference in size where the two people on the outside were clearly larger than the tiny person I had in the middle. And the tiny person in the middle is still able to push it to the ground. Now, did you ever go past the finger? No. Okay, yeah, sometimes they do need to use the whole hand for it, but why? Why is it that, because it looked like they were trying, or they were acting maybe. Why was Isaac able to push the thing down to the ground so easily?
Leverage. The force acting on it is weaker the further away you are from the person.
All right, so two things here. One, leverage, what did you mean by that?
Like the difference in the distance between the two, the person in the middle and the people on the ends, the longer that is, the, I guess with rope, I guess it would be, maybe you get less tension.
So sort of what Jacob was saying.
I think it's the same.
The tension in the rope actually was relatively constant throughout the whole thing.
Okay.
That if it were not, then you would see the rope moving this way.
The rope. Oh, sorry, go ahead.
Anna?
Okay, I think the direction of the force may have something to do with it, since they were pulling directly out to the side, there was nothing that was directly pulling the rope up the opposite direction that, I'm sorry, I don't know your name.
Isaac.
Isaac was pressing straight down, and there wasn't a force that was directly opposing that, and so maybe the forces added together and were pointing exactly in the direction of where the rope ultimately touched the ground.
And that's it in a nutshell right there. You want to add to that?
Oh, well, it's kind of something different, but I was just gonna say, like, I'm not sure how to put this in physics terms, but like, there wasn't enough, like, tension, I guess, in the rope to prevent him from.
It wasn't so much the amount of tension, because I think that the amount of effort that Nathan and Brian put into it, they were applying probably a lot more force to the rope than Isaac was. So it's not a matter of that. It is indeed the direction. So Nathan and Brian, were you feeling it before he even touched the rope?
The
I mean,
second
yeah.
or third time, yeah.
Yeah,
But the
first
first time we were just kind of like pulling, you know.
Okay.
couldn't
But,
talk.
so, who were they pulling it? Who were they trying to stop? Yeah. And one of them let go, the other one would go flying backwards. So they were actually holding each other up. Most of their effort was spent in keeping the other one standing, really, especially in the third one.
Thank you for not letting go.
Yeah.
That has not happened yet, but let's
Yeah.
hope that stays that way. So Isaac had no one opposing him to start out with. A couple other things that people sometimes mention, I just want to throw in there. Sometimes people think about the rope stretching. The rope this does not stretch significantly. I can take this point right here and I can pull really hard, and my hands, I don't think you're noticing my hands moving significantly far apart as I apply more force. Or it could be I'm just weak, which is part of it. But
Is there another factor of us like moving? Because we could have been moving downward without even thinking about it. You know, we're pulling straight across and he's pushing down in the middle. Do you think that there's a bit of a downward force that's gonna happen to us because we're balancing each other?
there's a certain amount of downward force acting on you because you're pulling in this direction and then you're pulling in that direction.
Okay.
Or the rope's pulling you in that direction, probably better wording. You're pulling this way, the rope's pulling you that way. But I don't think your center of mass dropped by
Yeah,
that far.
I got you.
So, a minor issue. If you had not actually moved down some as the rope went down, you'd be more apt to be pulled over, which I think happened.
Yeah.
Okay.
Now, as you went down, it looked like that it became, especially the third one, a lot harder at the very end.
Yeah.
Why?
I was literally putting my entire body into it.
Yeah, me too.
And just balancing.
Less that, think back to what Anna had said.
Direction of force.
Keep going.
Is there more, the angle of that direction? I mean, you know, I'm assuming it was close to perpendicular.
But who's close, where,
The opposing force, the force Isaac was applying.
it was perpendicular to the ground. I wouldn't say perpendicular, initially it was perpendicular to the roof. I missed part of what you're saying, sorry.
Well, I'm grasping at straws here. I'm visualizing forces in this direction and a force in this direction.
Okay.
And I'm saying it's like a right angle, at least starting out it is.
Absolutely, all right, so we start out with a force in this direction, a force in that direction, and a force down in this direction. And I am willing to bet that the force downwards did not match the force to the side.
Is that because at the middle it's the weakest?
No, it's not an issue of that. But as you got closer to the end, think about the direction of the pull. So this is at the very beginning, really not much of an issue to pull downwards.
Right.
But at the end, not drawn to scale. Recognize the two forces that are now being applied on the side that Brian and Nathan are exerting. There is now components in two directions. Now there is something, part of the force that is being exerted on the sides is countering him. And that's why it becomes more difficult, because the steeper the angle, the more of the force is upwards. Now, the big takeaway from this, one, forces we're not officially dealing with yet, but I like it as a gateway into vectors. Direction definitely matters. The other thing that mattered is as Nathan had said, they didn't put as much effort into it the first time. They would think well, especially since he was leaning back, or they both were leaning back on the third one. Size, probably better wording is magnitude, although sizes are we use sometimes interchangeably with it. So the magnitude of the force that was being applied mattered, and the direction mattered. And for any quantity, where magnitude and direction both matter, you're dealing with a vector. Now, there are a lot of vector quantities. Force is the vector quantity that we'll deal with more in chapter 4. But we do have various vector quantities that we will deal with in chapters 2 and 3. So let's first talk about how do you know that we're dealing with a vector. And actually, let's take a small pause here. What was the last thing I did last week?
We're talking about the difference between vectors and scalars.
Okay. So if I have a vector quantity of velocity, which is a chapter 2 thing, I need to somehow symbolize that it is velocity and not speed, because over here, this is the symbol for speed. So I need to somehow differentiate speed and velocity. Speed is a scalar quantity. Speed and scalar both start with an S. Velocity is a vector quantity, they both start with a V. That's not the way it always works, it just happens to work here. So I can represent this as a vector by putting a little arrow over it. The arrow always points to the right. It doesn't matter the direction of the velocity. That's the notation that says, hey, we're dealing with a vector. And then in this particular context, we are dealing with velocity. Some textbooks and other sources, instead of using the arrow over it, will use a boldface to represent it. I tend not to use boldface in class because it's not particularly easy to do. In class, I tend to do what I call the half arrow. I only half the head. And then, there is one case where I actually will do what I call the double print, but another way of representing the vector is like that. These are all different ways of notating that we're dealing with a vector. In class, this is the one that I use. On test, this is the one that I use because I'm using a word processing program and it will do that for me. All I have to do is vec v and it'll put this in delivery. All right, so vector map. You can add, subtract, multiply. Can't really divide vectors that I've seen. I'm sure there's some math person has come up with it, but not really much of a need for it here. So let's talk about addition. Now, how you add, there's a couple different methods of doing it, and it depends upon how you're starting. So let's talk about rectangular versus polar notation. If I want to represent this, let's say that this represents, I'm going to stick with forces, but it works for, this is just a specific case of a vector when I'm dealing with forces. It applies to any of the vector quantities. I need to somehow indicate that this force is. I have a 4 Newton force going that way. So how would I write, there's a 4 Newton force going that way?
4 newtons.
Like 4 Newton with the arrow above it?
With the arrow above it?
Above it or like to the right of it?
Well, if I put it above it, it sounds like it's more of a notation as opposed to indicating direction.
Okay.
I mean, this force, this is just telling me that there's a vector involved. It's not telling me, if I did that, that would say it's a 4 vector, but officially not a 4 vector. 4 vector means something different in physics. It's a vector of length 4, but it doesn't tell me direction quite yet.
Do you put the like north, east, west, south? Like would you put that's going east?
You could use degree.
So what would you do?
You're asking me.
Pardon?
I said degrees. You could use degrees or radian.
Yeah, so how many degrees is that?
0.
All right. Or 0 radians if you prefer. Any other suggestions? Oh, okay. Another way that we could also do it is 4 newtons to the right. This is too much writing though. Maybe not 0 degrees. This actually would be an expression, we had to throw in some parentheses and a comma, but this is polar notation right here. Another way of expressing the exact same thing, I could just say, well, you know, let's just make to the right. I'm going to call that I hat. So now I would write this as the force is equal to 4 newtons I hat. This has a nice advantage, is if I have the 4 Newton force going like that, I could just say, well, you know, let's just make that I hat. So my force is 4 newtons I hat. Now the question is this useful or not? That's a different story, but I hat does give us a nice advantage of being able to just indicate, I'll just say, in this case, to the right is I hat, and therefore anything to the right, I can just put an I hat afterwards, and I don't have to write out any of the rest of that stuff.
So are you saying the I hat only comes situationally, or as a situation?
When you are starting a problem, you after you read through the problem, you
Yeah.
then say, I'm gonna make that the I hat direction, or that the I hat direction,
Right,
or
okay.
you make I hat whatever direction you want it to be.
I didn't know if you were saying like, right now, we're gonna declare that I hat is to the right, and I was like, okay.
Declare it until I erase it.
Right,
Yeah, and it's not for the rest of the course, definitely not for the rest of the course, otherwise I just use X hat and Y hat and stick with brainwashing the math people put us through.
So you're saying I hat's a direction?
Yes, this hat on top of it, and if you use OpenOffice or LibreOffice equation editor, hat is the key word there. This is indication of what's known as a unit vector.
Ah,
A unit vector is a vector, so it has a magnitude and a direction. The direction of this vector is whatever I say it is, or in your own notes, whatever you say it is. And the magnitude is 1. That's called a unit vector for a reason. Now, they could have gone and called it a 1 vector, but they didn't, so you just have to live with it. So if I have a 5 Newton force going this way, and if I broke it down, let's put that at a 37-degree angle there. 36.8 something. It's a right triangle. So I have this vector, which is 5 newtons, 37 degrees, going along with what Ian had suggested. This is polar form. But defined in rectangular form, I break it into what are known as perpendicular components, figure out how far it's going, in this case, to the right, how far it's going up. And so I know this is going to be 5 times the cosine of 37 degrees. This will be 5 times the sine of 37 degrees. This is going to be about 4, this is going to be about 3. I take 37 degrees for a reason. So over here, why don't I just say to the right is I hat, so that takes care of this one. So I'm going 4 to the right, 4 newtons I hat. But I need to somehow define another direction here, because I have to the left and right taken care of. What about vertical? Absolutely. It's a 2-dimensional problem, so let me go ahead and bring in a second dimension. If it were a 3-dimensional problem, and I can't reduce it to a 2-dimensional problem, then I throw in k hat. Plus 3 newtons k hat.
oh, J hat.
Yeah, my
Okay.
J's look like J's and my eyes curl in the other direction.
Okay.
My J's are supposed to look like J's.
like a cursive J.
Yeah. Forward. Form. Rectangular form.
So,
Right?
okay, so the polar is just, you're designated with an angle as opposed to designating it with
Yeah.
2 triangle legs,
Yeah.
which, those 2 legs is the start of a rectangle.
Yeah. Pretty much.
Okay.
Other questions at this point? All right, so suppose I had a vector, let's take another force, let's put the hash, we'll make it a velocity. 3 meters per second j hat plus 4 meters per second I hat. And flip that order around. I'm gonna go ahead and keep this convention right here for now. What would this vector look like? I'm gonna pick a starting point. How far am I gonna be going, which way?
4 newtons of force to the right, and then 3 up.
Okay, not newtons in this case, but yes, the 3 up.
Sorry, meters per second, is that what it is?
Yep.
Okay.
Suppose could you have gone 3 up and then 4 over? Sure, why not? Yeah, commutative property holds, doesn't matter the order in which you add them in, you get to the exact same spot. Now, part of what this illustrates, didn't actually draw the vector. The vector from where it began to where it ended. This is the one time where I use the double print. When I'm talking about the resultant, when you add vectors, you get what is known as a resultant. Now, why they couldn't settle with the word sum, I don't know, but resultant is sum and resultant I use interchangeably here.
Dr. Fox, I have a question.
Yes.
I'm confused about how we ended up in the same spot. Like, I don't see why we couldn't have gone 3 meters per second to the right, either first or second, and then 4 up. Like, I don't know how we determined.
Because I was using this as my convention, and the 4 goes in the I hat direction, which is to the right.
Oh, we're continuing that convention.
Yeah, I circled it and
Okay, I thought it was situational for the problem, but it sounds like in general.
Really for any problem, on a test, for example, I could just put I hat and j hat like that at the top of the test and say this like it covers everything.
Okay, I understand.
But you really should define it per problem.
I see.
And I did it very briefly.
Okay.
Other questions right now? All right, so I've got this vector over here. Let's put it in polar form. What's my magnitude?
5 meters per second.
And the direction?